Good morning, everyone. My name is Khushi Yadav. Today I am going to present my topic Multithreading Model one to one, many to one, or many to many. I hope you will find the presentation interesting and informative. So let's begin. Operating system concurrency and threads. Multi-threading models. One by one, many to many. How operating system bridge the gap between lightweight users level thread and the kernel thread. A CPU actually executes and by the mapping strategy you choose still shape model runtime to design today. User thread kernel. Introduction. Why the mapping between threads matters. Background. A thread is the smallest unit of CPU executions, a single sequential flow of instruction within a process. Modern software rarely runs as one flow. Browsers render, fetch, and the response to input simultaneously. Servers handles throw of requests at once. This concurrency is built on thread, but every operating system must decide exactly how those threads are created, scheduled, and ultimately run of physical core. Importance. Application create threads in a user space through a thread library, but only the kernel can actually place work on a CPU. The relationship the OS defined between these two layers, how many user threads correspond to how many kernel threads, determine performance, scalability, and how gracefully a system handles blocking operations like disk or network input. Overview. Three classification strategy answer this question: many to one to one, and many to one. Core concept. Two layers, one question. How do they connect? First, user level threads. Create and manage by a thread library running above the kernel, fast to create and switch between but invisible to the OS scheduler. The kernel only ever sees the process. Kernel level thread managed directly by the operating system, heavier to create, but the kernel can schedule them independently across multiple CPU cores for true parallel execution. Multithreading models is simply the rule that define how users' threads are mapped onto kernel's thread. Detailed explanation part first. The many to one model. How it works? Every user level thread created by an application is mapped onto a single kernel thread. The thread library performs all scheduling entirely in user space, so the operating system never sees more than one thread per process. K characteristics. The thread creation and context switching are extremely fast. No system's call is required. Second point, if one thread issue a blocking system call, the entire process blocks since the kernel is unaware other thread exists. Third point, no true parallelism. The process can use more than one CPU core simultaneously even on multi-core hardware. Example: early Java Green Thread JDK 1.1 and GNU Portable Threads. Detailed explanation Part 2: One-to-one and many-to-many model. Firstly, one-to-one model. Each user thread maps to its own dedicated kernel thread. The OS scheduler manages every thread directly, enabling genuine parallel execution across multiple core. First point, two parallelism. Multi-threads run simultaneously on a separate cores. Second point, a blocking call in one thread never stalls the other. Third point, higher overhead. Each thread requires a kernel resource, so most OSes cap the numbers of threads a process may create. It is the example Linux, NPTEL, and modern Windows threads. Second, many-to-many model. Multiplexer many user thread onto a smaller or equal pool of kernel threads. The library can create as many threads as an application needs will the kernel still run several in parallel. Multicore, a variation, the two-level model, add the option to bind a specific user thread directly to one kernel thread when needed. Example of many model: Solaris, Legacy, and the conceptually similar to Go's Gorotine scheduler. Applications: real-world system built on these models. Linux and Windows threads. One-to-one. NPTEL on Linux and Win32 thread. API map every application thread straight to a kernel thread, giving production servers real multi-core parallelism. Many-to-many. Gortines. Go's runtime multiplexes potentially millions of lightweight Gortines onto a smaller, tunable set of OS threads. Gomex procs and the Modux MN scheduler. Application of many-to-one. Legacy GVM Green Thread. Early Java pre 1.2 on Solaris scheduled all Java threads purely in user space, trending parallelism for portability before native threads arrived. Many-to-many Java Virtual Threads Loom. Modern Java reintroduces lightweight virtual thread multiplexed onto a pool of kernel threads built for massive input-bound concurrency. Advantages and benefits. For each model, optimize for many-to-one. Minimal kernel overhead per thread. Extremely fast creation and context switch. Fully portable, no OS threading supports required. Advantages and benefits of one-to-one. True hardware level parallelism. No single blocking calls stalls the process. Simple predictable scheduling. Semantics. Advantage and benefits of many-to-many. Scalar to hug thread counts cheaply. Still exploits multiple cores in parallel. Runtime can rebalance load dynamically. Challenges and limitations. Every model trades away something. Many to one. Problem: a single blocking system called freezes the entire process. No way to use more than one core. Mitigation: redesigning blocking input as non-blocking asynchronous call. The library can intercept one-to-one problem. Kernel thread creation is costly and most OSEs impose a hard ceiling on thread count limiting scales. Mitigations: use bounded thread pools instead of one thread per task to cap resources uses. Many to many problem. The user space scheduler itself is complex and implement correctly and can be hard to debug the tune. Mitigation: adopt mature battle tested runtimes. Go Loom Takeo rather than building a scheduler from scratch. Now we learn about the future scopes and trends. The industry circling back to many as core counts keep climbing and workloads become more input and network bound both operating system. Language runtimes are converging on lightweight, multiplexed, trending, and the many to many idea. Rebuilt with far smarter scheduler than the 1990 green thread that first tried it. 1990s green threads. Early many to one JVMS proves user space scheduling is fast but cannot use multiple cores. 20s native one-to-one thread, Linux, NPTEL, and Win32 thread standardize one-to-one for reliable simple parallelism. 2020s में virtual threads revival, Java, Loom, Go, Gogurtans, and Run Async runtimes bring many to many back with mature MN scheduler. Now conclusion. One question, three answers, and the loop back. Care takes away. Many to one lightweight and portable, but one blocking call holds everything. One to one true parallelism at cost of per thread kernel overhead. Many to many multiplexed flexibility and balanced modern runtimes now favor. We opened by asking how many user thread kernel should actually see. The answer the industry keeps arriving at. From Gorat teens to virtual thread is as many as applications needs multiplexed onto only as many kernel thread as the hardware can truly run in parallel. This is about multithreading models, one to one, many to one, and many to many. Thank you for everyone for listening. I hope you found my presentation useful. If you have any question, I will be happy to answer them. Thank you so much.